Okay, in this session, we'll discuss about the two popular analog filters because the IIR filter can be designed in various steps to design analog filters, Butterworth filter and Chebyshev filter. Because the IIR design is based on analog filters. Analog filters. From the analog filter specification, from the analog filter specifications, we have to derive the transfer function h of s given specification, then derive transfer function h of s, then convert your h of s into h of z. So the two popular analog filters are one is a Butterworth low pass filter and second one is Chebyshev low pass filter. Depending upon the frequency response, based on the frequency response, we can classify the filters into low pass filter LPF, high pass filter, band pass filter, band stop filter. Okay, so based on the frequency response, the filters can be classified into four types. So now we'll discuss about the magnitude response of Butterworth low pass filter. Butterworth low pass filter. The magnitude response for various order of the filters. The order is the system function. The order is number of poles. N is the order of the system. Order of the system. Okay. If you see the magnitude response of the Butterworth low pass filter, okay, what the ideal one? The ideal one will be, this is the ideal characteristics of, so this is 1. This is the ideal characteristics of Butterworth low pass filter. Okay. So, but in real time, in practically, you will not get the ideal one. You can only closer to the ideal one. You can have an approximation near to the ideal one. So there will be tolerable ripples in the pass band and stop band. So this is already last videos we discussed about it. In this low pass, this is a pass band region. Okay, so there will be ripples in the pass band and there will be ripples in the stop band. So with respect to low Butterworth filter frequency response, when you go for the higher order, what about if n is equal to, for example, 10, n is equal to 4, n is equal to, we'll take 2, n is equal to 1. When you go for the higher order filters, you can get a closer to the ideal one. For example, this is your, so closer to the ideal one you can get. Closer to the ideal one. Normally, the frequency response characteristics will be, this is for Butterworth low pass filter. Generally, there will be a, this is the ideal one. So there will be a ripples in the pass band. There is a transition band. There will be a ripples in the stop band. So these are the ripples in the stop band. So there will be this is 1. This is your ripples in the tolerable ripples in the pass band, 1 plus del p and 1 minus del p, and 1 by root 2, it is equal to 0.707. So for example, this is 0.707. Okay, this is your cutoff frequency. This is your cutoff frequency. This is your pass band edge frequency. This is your stop band edge frequency. Okay, so this is your omega. Remember that. So this is general pass. This is our pass band. Okay, this is your stop band. This is your transition band. This is your transition band. This is your transition band. So the transition band, that is omega s minus omega p. Okay, this omega p is the pass band edge frequency, omega s is the stop band edge frequency. So the pass band is the bandwidth. So bandwidth is equal to omega p, pass band edge frequency. So this is our cutoff frequency. Okay, the 1 by root 2.707 is the cutoff frequency. So this is a pass band edge frequency, the stop band edge frequency, ripples in the stop band, ripples in the pass band. When you go for Butterworth low pass filter, because there are two types of analog filters, based on the frequency response, we can compare. So the Butterworth filter, how the frequency response, when you go for the higher order filters, n is equal to 10, it will be closer to the ideal one. You can get the ideal one. Similarly, if n is equal to 4, we'll take n is equal to 4. So it's somewhat closer. Again, it will be some closer to the closer to the n is equal to 4. Then n is equal to 2. So n is equal to 2. This is n is equal to 2. N is equal to 1. This is n is equal to 1. So this is n is equal to 1, n is equal to 2, n is equal to 4, n is equal to 10, for example. So in n so n is equal to 10 will be closer to the ideal one. So n is equal to 10. Okay. So this is 1 by root 2, which is equal to 0.707. So this is your cutoff frequency. So this is your ideal response. Ideal response. Okay, then this is a magnitude squared magnitude response h of j omega. This will be this is omega. This is a frequency response of Butterworth filter. This is the frequency response. Frequency response of Butterworth low pass filter. So this is a pass band, this is a stop band. So then this is stop band, this is a transition band, omega. So these are the specifications of the filter, analog filters. So what are the specifications of the first one? What are the specifications of first step? The given specifications of the filters. So the del P, del S, del P, del S, and what is the order of the filter? Then what about the omega p, ripples in the pass band, ripples in the stop band, pass band edge frequency, stop band edge frequency, the cutoff frequency. Okay, these are the given specifications of the low pass filter. Omega c. So ripples in the pass band, ripples in the stop band. So now we can write the derivation. So the magnitude we can write. So the magnitude response, the magnitude squared response of Butterworth low pass filter of order n, is defined as h of omega squared is equal to 1 divided by 1 plus omega by omega c of 2n. So this can be represented as, so the omega c, n is the order of the filter. N is the order of the filter. Omega c is the 3 dB, is a minus 3 dB cutoff frequency. So 3 dB frequency or cutoff frequency. Omega p, so this can be written as 1 divided by 1 plus epsilon squared of omega by omega p of 2 power n. So this is a 3 dB cutoff frequency. With respect to passband, so what is actually the passband, which is equal to passband edge? This is a passband. Okay, this is a passband. So omega by omega p. So what is the epsilon here? The epsilon is nothing but a ripples in the passband, and stop band. So is a radian cutoff frequency. Omega c is the radian cutoff frequency. So omega p is the passband edge frequency. So 1 by 1 plus epsilon square is a band edge value. Okay. So attenuation now. So many parameters in different books, different notations are used. So we'll discuss one by one. Attenuation. Attenuation can be defined as log 10 the squared magnitude square response. If you take a 10 log 10 of magnitude square response, it will be attenuation. So the attenuation in dB can be defined as, so this will be, so you can write this one, h of omega squared will be, substitute this one, h of omega. So a by b, so a by b in terms of log you can write log a minus log b. So log a is log 1, so 10 log 1, so you can write 10 log 10 of, so what is the h of omega? 1 divided by 1 plus omega by omega c or 2n. So this can be written as 10 log minus log a minus log b. So 10 log log 1 plus omega by omega c power 2n 10. So you can write this will be 0, 0, this term will be 0. So attenuation in dB minus 10 log 10 1 plus omega by omega c omega c 2n. So minus will be cancelled. So attenuation in dB is equal to 10 log 10 1 plus omega by omega c of 2n. So the attenuation, sorry, here 1 plus uh, 10 log 10 minus 10 log 10 plus omega by omega c or 2n. Okay, so 10 log 10 1 plus omega by omega c for 2n. So generally the h of, how do you define the transfer function? H of s can be defined as 1 by s plus p1 into s plus p2 into s plus p3 up to s plus pn. Okay, so h of s can be written as 1 divided by, okay, an, there is an s power n, an s power n plus an s power n plus an minus 1 into s power n minus 1 plus a1s plus a naught. H of s, the transfer function, can be defined as the denominator, the poles. Okay, so h of s equal to 1 divided by a naught plus a1s plus an power s power n. For n is equal to, we'll write the all coefficients of a naught a1, a naught a1, a2, a3 up to, I'll write a6, n is equal to 6. If n is equal to 6, so n is greater than or equal to 1 and less than or equal to 6. For this uh, n values, the denominator polynomial coefficients, you can refer this table. From the following table we can uh, take the coefficients of the denominator polynomial coefficients of the normalized Butterworth filter. So the polynomial coefficients, the polynomial coefficients, the polynomial coefficients of the normalized, the normalized Butterworth filter may be obtained from the following table. So for example, n is equal to here 1. So the a1 value will be 1. a1, a2, a3, a4, a5, a6. But a0 is equal to 1 for all n. For all n, it will be for all n. So either capital M or small n out of the order. For all n, the value of a0 is equal to 1. If for first order, the a1 coefficient will be 1. For second order, if n is equal to 2, then the a1 will be 1.4142136 and a2 will be 1. If we say n is equal to 3, then it will be 2, this also 2 and a3 will be 1. And if n is equal to 4, this is 2.6131, this is 3.4142 This is 2.6131. Then A4 will be 1. If n is equal to 5, A1 value will be 3.236 and it will be 5.236 and A3 will be 5.236 and this will be A4 will be 3.236 and A5 will be 1. When is equal to 6, this A1 value will be 3.8637. This is 7.4641. Then A3 will be 9.4146. 9.410 and A4 will be A1 3.82, A3, A4 will be A1, A2 7.46, A3 then 7.464, then 3.86, then A6 will be 1. However, only the poles in the left hand side only, in the S plane only, it is used to derive the H of S in order to preserve the stability. So now you normalize, the next step is, so that how that system transfer function for the unlock filter can be defined, and depending upon the order of the filter, the coefficients, polynomial coefficients can be taken from the table. The next one, what do you mean by frequency denormalization? So these are the normalized transfer function. So the normalized transfer function is converted to 1 with the required frequency characteristics. So it may be a low pass, or it may be a high pass, or it may be band pass. So this technique, required frequency characteristics. This technique is called frequency denormalization. So analog filter design. So next one is with respect to the order of the filter, what are the polynomial coefficients? Then you convert the normalized transfer function to the required frequency characteristics. So from the normalized low pass prototype to, you have to convert either low pass or high pass, whatever. Okay. So you have to transfer from prototype. Okay. Normalized low pass filter prototype to, you have to convert to low pass filter. The normalized low pass prototype to denormalization are doing. For low pass, you put a substitute in the H of S. In H of S, substitute for S. In this H of S, put S is equal to S by omega C. Similarly, for high pass filter, if it is a high pass filter, low pass filter. For high pass filter, put S is equal to omega C by S. For band stop filter, put S is equal to, that is S into omega CH minus omega CL divided by S squared plus omega CH into omega CL. If it is a band pass filter, it's a band pass filter, put S is equal to, so S square, this will be S square plus omega CH into omega CL divided by S into omega CH minus omega CL. Okay, so frequency denormalization. So this is a frequency denormalization you have to do. So with respect to order of the filter, you have to write the coefficients. So the transfer function can be defined as given from the given specification. Find the order of the filter, then write down the h of s function, then from the h of s to h of z. Okay, so then frequency denormalization. Finally, we have to find out the poles of the filter. In general, normally the poles, the angle of the poles, how it is denoted, angle of the poles determination, the poles how it is located, denoted by pi k. So where angle of the pole is denoted by angle of the kth pole. The angle of the kth pole is denoted by pi k, where k is equal to 0, 1, 2 up to 2n minus 1. Okay, so which are all located on the circumference of the unit circle. Circumference of the unit circle. So this is a unit circle. Unit circle. So how the poles are located? So this is a S-plane. How the poles are located? So these are the poles are located on the circumference of the unit circle in the S-plane. This is S-plane. So if the angle of the kth pole is denoted by pi k and all these are located on the circumference of the unit circle of your on S-plane. So if k is equal to, that is n is equal to maybe odd or n may be even. So in that case, if it is odd, the location of the angle of the pole pi k is equal to k pi by n, or n is equal to odd. Similarly, if n is equal to even, then the angle of the pole kth pole will be k plus 1 by 2 of pi divided by n, where n is equal to even. So n is equal to odd and n is equal to even, the kth pole how to determine. Okay. For example, the transfer function h of s, okay, 1 by a naught plus a1s plus a2s squared plus a3s cube plus a4s4. So what is n? N is equal to 4, fourth order. So n is equal to fourth order. So how do you write the system function? A naught is always 1 for all n. Okay, so 1 plus, what is it? Fourth order filter. If n is equal to 4, okay, sorry, if n is equal to 4, see, n is equal to 4, what are the coefficients? If n is equal to 4, What are the coefficients of A1, A2, A3, A4, 2.6, 3.4, 2.61? So now, see, so how do you write the transfer function now? 1 plus 1, this is A0 is 1, then A1, what is A1 value? 2.6 into S plus A2 values 3.4 into S square, A3 values 2.6 into S cube, and A4 is 1. Okay, so S power 4. So now N is equal to even. So the formula for even 5k is equal to, so k plus 1 by 2 into pi by 4. So this is a formula. See, by k plus 1 by 2 into pi by n for n is equal to even. To determine the number of poles and angles. So to determine the number of poles and angles. So now, so pi is equal to, so what is the k value? K is equal to 1 comma 0 comma 1 comma 2 comma, so what is the value? K value? N minus 1. Okay, so we can enter now n minus 1. K is equal to 0 1 2 2n minus 1, 2n minus 1. So n is equal to 4, no? So 2 into 2, 2 into 4, minus 1. So 8 minus 1, so 0 1 2, so 8 7 up to 7. K is equal to, so 2n minus 1, so up to 7. For example, so what is the pi value here? Pi 0, 0, k equal to 0. Determine k equal to 0, pi 0, then pi 0 will be pi by 2, okay, by 4, so pi by 8, pi by 2 into pi by 4, so by 4 which is equal to pi by 8. So how do you represent the angle? So e power j pi, I'm written as cos pi plus j sin pi, and write this as poles. So cos pi, so that is a pi by 8. What is the degree? The angle is 28 point. So pi by 8, find out the angle. So degree, pi by 8 by 8 will be 22.5. Okay, but if you see here, this for stability purpose, the poles, because this is 0, this is 90 degree, this is 180 degree, this is 270 degree. So that for stability, we have to consider only on left hand side. Okay, the left hand side of S plane. So this left hand side, so between 90 and 270, between 90 and 270 degree only we have to consider for stability. Okay, so these are the fundamental concepts of Butterworth filter. Okay, now we'll to in order to find the order of the system, in some other books the notations will be this. Also I'll tell you, to find some books, to find the order of the system, to find the order of the system function. So you know the magnitude response of the frequency response of the Butterworth low pass filter. Butterworth low pass filter. So So this is your omega p. This is omega s. There is a ripples in the passband, no? Omega s. So this will be ripples in the passband, ripples in the passband attenuation. So alpha p. So this will be alpha s. There is alpha s. So demand response. Okay. So this term in some 1 plus square root of 1 plus lambda square, let it be. I'll tell you the ripples in the pass band and ripples in the stop band is denoted by 1. This is 1 by square root of 1 plus epsilon square. Okay, so this point omega, this is omega c point 1 by root 2.707. So this is 1 by root 2.707. Okay, so this one, this will be omega c, omega c. So the epsilon and this lambda is replaced in the pass band and stop band. So the magnitude response h of omega is equal to 1 by, so already we know 1 by omega c or 2n. Okay, for pass band and for stop band we'll solve. So the squared magnitude response. So this can be the, so the squared magnitude response is equal to, including the ripples, this is the ideal one. If you include the ripples, then the equation will become the ripples in the pass band and stop band. So omega by omega p the r2n. So what is the attenuation in the pass band now? So already we derived. So 10 log 10. Okay, 1 plus epsilon squared omega by omega p up to n if you include the ripples in the pass band and stop band. Okay, so for pass band, so you consider for pass band, for pass band, for pass band. So if omega equal to omega p, omega equal to omega p. So now this term will become, so omega is equal to omega p means omega p by omega p. So it will be cancelled. So it will become 10 log 10. Okay, 1 plus epsilon square. This term will be cancelled. 1. So this is your alpha p. So if you take antilog on both sides, take antilog on both sides. So directly you can remember the formula, but how we are deriving, how the magnitude response, frequency response represented by 1 by 1 plus omega c of 2 per n. If we include the ripples, epsilon is a, what is epsilon? Ripples in the pass band and stop band. So now for pass band, if we consider pass band, then omega is equal to, you substitute omega p, so this term will be 1 plus epsilon squared. So take antilog on both sides. Okay, then the epsilon squared is equal to 10 power, okay, 0.1 alpha p minus 1. So this is a, take antilog on both sides. So it will become 1 plus, so you can take 1 plus epsilon square, which is equal to 10 to the power 0.1 into alpha p. So epsilon square is equal to this one. So epsilon is equal to square root of 10 to the power 0.1 alpha p minus 1. So this is your epsilon. Okay. Similarly, understand? So antilog on, take antilog on both sides. So you will get epsilon. Similarly, you take for stop band. for stop band, the attenuation in dB. So stop band is attenuation. Stop band is attenuation. Attenuation means attenuation dB. This is equal to 10 log 10 of this is h of omega squared. So which will be here you are considering omega equal to omega s. So attenuation in stop band, so minus alpha s equal to minus 10 log 10. So what is 1 plus the representation in the stop band will be omega by omega p, okay, into 2 per n, So 1 plus omega equal to omega s. So you can write 1 plus epsilon square omega s by omega p of 2 per n, which is equal to 10 to the power 0.1 alpha s. So now omega s by omega p for 2n, which is equal to 10 to the power 0.1 alpha s minus 1 divided by this epsilon square. Minus this become minus 1, so epsilon squared here. Okay, what is epsilon square? So omega s by omega p, omega s by omega p are 2n, which is equal to 10 to the power 0.1 alpha s minus 1 divided by what is epsilon? Already epsilon is we derived first passband, no, 10 to the power 0.1 into alpha p. So 10 to the power 0.1 into alpha p minus 1. Then you can simplify omega s by omega p of n, which is equal to square root of 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1. So now n is equal to n, you can take log on both sides, n log of omega s by omega p, then write log of, okay, so this will be 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1. So now n is equal to log of 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1, okay, divided by log of omega s by omega p, okay. So now you can simplify, you can rewrite that is n is equal to log of lambda by epsilon divided by log of 1 by k. What is lambda? What is k now? So k is equal to omega p by omega s. Omega p by omega s. K is equal to omega p by omega s. What is omega c? So what is lambda? Lambda is equal to, so what is lambda? Square root of 10 to the power 0.1 alpha s minus 1. What is the epsilon? So square root of 10 to the power 0.1 alpha p minus 1. Okay. So and one more, the cutoff frequency can be defined as omega p by epsilon of 1 by n. So all these formulas have to remember to solve the problem in IIR. Okay. So for example, so how to find the, because in this session how to find the order of the filter. So either because different books they use different notations. I have given both the frequency response characteristics. So for example, problem order determine the order of the filter. Determine the order of the filter. Specifications are the passband alpha p is equal to 1 dB. Attenuation in the passband is given. Attenuation in the stopband is given 30 dB. Okay, then stopband its frequency is 200 radians per second, and omega. So this is omega p. Omega p is given. Omega s is equal to 600 radians per second. Okay, find the order of the system. So what is the order system formula? N is equal to log of square root of 10 to the power 0.1 alpha s minus 1 divided by 10 to the power of 0.1 alpha p minus 1 divided by log of omega s by omega p. Okay, so substitute the values alpha s, alpha p. So what is it? 30 dB. Okay, so how do you convert the dB formula? So what is it? How do you define? So n is equal to log of square root of, what is alpha s here? Alpha s is attenuation in stop band. So attenuation in stop band is 30 dB. So 30 dB. So attenuation is 10 to the power 0.1 into attenuation in stop band 30 dB minus 1 divided by 10 to the power 0.1 into alpha, and this attenuation in the pass band is 1 dB. So minus 1 divided by log of stop band frequency. This is a H frequency. Stop band and pass bands are 200 and 600. So 600 by stop band H frequency by the pass band H frequency 200. So n is equal to log of, you get the square root of 10 to the power 3. This will be 10 to the power 3 minus 1. Okay, by 10 to the power 0.1 minus 1. So this will be 3. So we'll get the denominator will be n is equal to log of square root of 10 to the power 3 99999 divided by 10 to the power 0.2. So use calculator, and this value will be 0.258 and divided by log of 3. So which is equal to log of this value will be log of 62.226 divided by log of 3. Log of 3 you will get 1.793 divided by log 3 will be 0.477. Use calculator cross check, and 3.75. So round off the value, which is approximately equal to 4. N is equal to 4. So this is the order of the filter. Order of the filter. So first you need to find out the order of the filter. Then form the transfer function, analog transfer function. Then convert analog to digital transfer function. Okay. So and here one more. I hope that you understood that gain in dB. So gain in dB is equal to, how do you represent gain in dB? 20 log 10 A. A you can write 10 to the power. So 20 log 10 to the power gain in dB by 20. So this is why how to find the value of A. So depending upon the given specification parameters, we should be able to find out, okay, the order of the filter. So one more problem, order of the filter. Determine the order of the filter. Alpha p equal to, for example, alpha p equal to 2.5 dB and alpha s equal to 30 dB, and the passband H frequency is 20 radians per second. This is also a problem. Okay, omega s is equal to 50 radians per second. So how do you find out the order of the filter? So n is equal to log of square root of 10 to the power 0.1. Alpha s is 30. Again same 10 power 3. Otherwise you write 0.1 into 0.1 into alpha s. So what is alpha s? Alpha s 30 dB into 30 dB minus 1 divided by 10 to the power 0.1 into alpha p. Alpha p is 0.25. So 2.1 into 25 dB. So minus 1. So divided by log of, so omega s by omega p. Okay, omega s by omega p. So what is it? Stop band edge frequency 50 by 20. Okay, 50 by 20. Log of omega s by omega s. So what is omega s? 50 by 20. So 50 by 20 millions per second. So 5 by 2. So 5 by 2.5. So you can simplify log of 2.5 denominator term, and the numerator term is log of square root of 10 to the power 3 minus 1 divided by 10 to the power 2.5, 2.5, 0.25, 0.25 minus 1. Okay, so here, so which is equal to log of 2.5. So log of this is 90 log of square root of 999. So use calculator and cross check. I have cross checked all the values. So by using calculator 0.0778 this value. So step by step you do, you so don't do any mistakes. So log of 2.5. So again this value will be log of 35.83. Cross check all the values. Log of 2.5 is equal to 1.555, 0.39 equal to 3.97. So approximately the order will be 4. Round off. N is equal to 4. So now n is equal to 4 means you know how to take the transfer function. So a0 plus a, this is a 1 by a0 plus a1s plus a2s square plus a3s cube plus a4s power 4. So this is the order of the filter. So once you find the order of the filter, then form the transfer function. You know what is a0 value is equal to 1 for all n, and find the polynomial coefficients are a1, a2, a3, a4. So up to 6 I given the table, the polynomial coefficients. From the table you can take the coefficients, then Once you from the specification, given specification, find the order of the filter. Once if you find the order of the filter, then you can form the transfer function. So in the transfer function, so the coefficients a0 is 1 for all n and a1 a2 all the other polynomial coefficients you can find out from the table and form the h of s transfer function. Then convert this h of s transfer function into h of z either by using bilinear transformation method or impulse invariant method. Then realize the h of z. Okay. So, but for a given frequency specification, the analog frequency digital frequency conversion also, you can refer the formulas. So, we'll take complete problem from the specification. So, normally, what are the design steps we have seen? Okay, here I will summarize the uh, how to design the IIR filter from an analog filter. Okay, the first step, here, the first step. So for the given normalized transfer function, h of s, the normalized transfer function h of s will be given. For example, 1 by s square plus 1.414s plus 1 transfer function is given. So for the normalized transfer function of analog filter is given. The complete design flow for the IIR filter design. So convert this analog filter to a digital filter first with the cutoff frequency. For that we have to do first step is pre-warping. Pre-warping is so frequency warping means frequency distortion because of the non-linearity between the omega and omega. So first step we have to do pre-warping. This is a frequency warping. So you have to convert this analog to digital frequency. So pre-warping has to be performed. First pre-warping has to be performed, which means convert analog frequency. Okay, convert your analog frequency into digital frequency using bilinear transformation method or impulse method. So the second step, first pre-warping, second one, convert your normalized analog transfunction, denormalization. This is called frequency denormalization. Frequency denormalization. First pre-warping, then convert the normalized low pass prototype into low pass or high pass, band stop by using that is called frequency denormalization. Then convert this analog transfer function into digital transfer function. Digital transfer function h of z by using either bilinear method or impulse invariant method. So the given specification, given analog specification, the given analog specification. So here the specification analog filter specification. Analog filter means either you can it may be Butterworth or another filter is Chebyshev filter. So in this session, Chebyshev filter. In this session we discuss only Butterworth. The next session we discuss about Chebyshev frequency response. So in the Butterworth frequency response, depending upon the frequency response, based on the frequency response, the Butterworth may be low pass or high pass or band pass or band stop filter, band stop filters. So given specification, so to do the design of IR filter, pre-warping, then frequency denormalization, then convert H of S to H of Z, then finally realization. Finally, the realization of IIR filter. Either you can use direct form 1 or direct form 2. Better use direct form 2 directly. Direct form directly can do from direct form 2. Okay, so in the next session, we'll take complete specification of analog filter, either low pass or high pass. Then we can derive, and finally we can convert into H of Z, and finally we can realize. So from this first step to last step, the next section will take one problem and how to solve. Okay, thank you.